Dear students, welcome to the next lecture on colloids. In the previous lecture, we have discussed about electrical double layer, zeta potential, and the electrokinetic phenomena in colloidal particles. Due to the presence of electrical double layer at the interface of the dispersion medium and the dispersed phase in a sol, the sol particles show certain interesting phenomena like electrophoresis and electroosmosis. These are known as electrokinetic phenomena. When a colloidal solution is placed in an electric field, the electrically charged colloidal particles migrate towards the oppositely charged electrode, which is called as electrophoresis. Another interesting phenomenon shown by the colloidal particles is the sedimentation potential or Dawn effect. When the particles are allowed to settle under the influence of gravity, a potential difference develops between the upper and lower layers of the liquid column through which they fall. This potential difference is known as sedimentation potential or Dawn effect. In the case of electrophoresis, the migration of the charged colloidal particles takes place in the presence of an electric field. Sedimentation potential takes place in the absence of an electric field when the particles are allowed to settle under the influence of gravity. When the particles of a suspension fall under the influence of gravity, the interfacial fixed and the diffuse layers are displaced with respect to each other, and the particles carry their fixed charge towards the bottom of the liquid column, leaving behind the diffuse layer at the upper portion. Hence, a potential difference is developed, and this potential difference is called the Dawn effect or sedimentation potential. If the colloidal particles are negatively charged, as they fall down, the excess negative charge will come to the bottom of the liquid column, and the top portion of the column will acquire a positive charge. Similarly, if the colloidal particles are positively charged, they carry their fixed charge towards the bottom, so that the bottom of the liquid column becomes more positive, and thus a potential difference is developed at different heights of the liquid column through which the particles are allowed to settle. This is known as Dawn effect or sedimentation potential. Next is Donan equilibrium. Donan equilibrium is otherwise called Gibbs-Donan equilibrium. It describes the equilibrium that exists between two solutions that are separated by a membrane, and the membrane is constructed in such a way that it allows the passage of certain ions through it, whereas it does not allow certain large ions to pass through it. That is, the membrane is selectively permeable to some of the ions. Donan equilibrium is named after the scientist Frederick George Donan, who proved the existence of this equilibrium in biological cells. The impermeability of the membrane is typically related to the size of the ions. A large ion cannot pass through the pores of the membrane, whereas smaller ions are diffusible. The diffusible ions reach a special type of equilibrium in which the distribution on two sides of the membrane is unequal, and such an equilibrium is called Donan equilibrium or Donan membrane equilibrium. At this equilibrium, the osmotic pressures of the two solutions will be different. And also a difference of potential is developed between the two sides of the solution because of the unequal distribution of ions. And this potential is termed as membrane potential or Donan potential. Let us consider an example in which a solution of sodium chloride is separated by a dialysing membrane from a solution of NaR, where R minus is the large non-diffusible anion. Let the initial concentrations of NaCl, that is the concentration of Na and the concentration of Cl, Na plus and Cl minus be C1, and the initial concentration of Na plus and R minus be C2. C1 is greater than, consider that C1 is greater than C2. As the membrane is permeable to both Na plus and Cl minus ions and not permeable to R minus ions, in the equilibrium state, Na plus ions will diffuse from the NaCl side to NaR side, that is from the left side to right side according to the diagram. Cl minus ions will also diffuse from the left to right side, and R minus ions remains constant at the right side. If the amount of Na plus and Cl minus ions that diffused through the membrane is X, when the equilibrium is established, the concentrations will be the concentration of Na plus and Cl minus at the left side will be the initial concentration C1 minus the concentration of ions that has migrated to right side, that is we get C1 minus X. The concentration of Cl minus will also be C1 minus X at the left side. At the right side of the membrane, the concentration of R minus remains the same, C2, and there are already C2 Na plus ions present at the right side, and when an amount of X ions migrate from left to right, the equilibrium concentration of Na plus ions at the right side will become C2 plus X. Initially, the concentration of Cl minus at the right side is 0, and at equilibrium state, the concentration of Cl minus becomes X. And if the solutions are assumed to be dilute, the equilibrium molar concentrations of NaCl should be same on both sides of the membrane according to the thermodynamic equilibrium. So initially C1 is greater than C2, and if we take the dilute solutions, equilibrium is established when the concentration of diffusible ions becomes equal on both sides. Thus we write the concentration of Na plus into the concentration of Cl minus at the left side equal to the concentration of Na plus into the concentration of Cl minus at the right side. And substituting the values of concentrations, we get C1 minus x into C1 minus x is equal to C2 plus x into x. It is same as C1 square minus 2C1x plus x square is equal to C2x plus x square. The common term x square gets cancelled on both sides, and C1 square can be written as x into C2 plus 2C1, or x is equal to C1 square divided by C2 plus 2C1. On rearranging, we can write as x by C1 is equal to C1 divided by C2 plus 2C1. And the fraction x by C1, that is the LHS, gives the fraction of NaCl that diffuses into the NAR side at equilibrium. That is, X ions diffuses, the X represents the concentration of ions that diffuse to the right side, and C1 being the initial concentration. The term X by C1 gives the fraction of NaCl that diffuses into NAR side. And from this equation, x by C1 is equal to 1 by 2 only when C2 is equal to 0. X by C1 is equal to half means half of the Na plus and Cl minus ions are migrated to the right side of the membrane. And this happens only when NAR is absent. That is, in the presence of a non-diffusible ion, the concentration of Na plus and Cl minus will not be same at both sides of the membrane. The distribution of the diffusible ions is not equal on two sides of the membrane at Donan equilibrium. And larger the concentration of NAR, greater will be this inequality. Donan equilibrium is of great significance in biological systems. In the case of RBC membrane, it is permeable to Cl minus bicarbonate ions but impermeable to large proteins, protein anions. Hence, the distribution of diffusible ions between the contents of RBC and the surrounding plasma is governed by Donan equilibrium. It is also applicable in the case of artificial kidneys, which have thin dialysing cellulose membrane, impermeable to plasma proteins and other cellular components, but permeable to small ions in the blood. Donan equilibrium finds other applications in the case of dyeing animal fibers by acid dyes, leather tanning, etc.